So let's go ahead in this video and we'll design an arithmetic logic unit. Now if you get stuck anywhere through this video, remember that you can always open up the actual design and simulate it for yourself, and sometimes it's much easier to see what's happening by simply clicking on it, and you can look and you can follow through the zeros and the ones through the entire circuit. So let's go to it. It's a long video, but stick with it and you'll get there. So let's start off our ALU by looking and seeing how we can add two binary numbers. So to keep it simple, we'll only look at a 2-bit number. So we've got two inputs, an A and a B. So there's four possible combinations. We can have 0, 0, 0, 1, 1, 0 and 1, 1. And we're going to add them together to get a sum and also a carry out. So when we add 0 and 0, we get a 0 for the sum, and we get a 0 carried out to the next most significant bit. When we add 0 and 1, we get a 1 and a 0, we get a 1. When we add 1 and 1, well, the decimal addition for 1 and 1 for this binary would be a number 2, and the number 2 would give us a binary 0 and 1. So we've got a 0 carry 1. Now we can see how we're going to build this if we just look at the truth tables for this sum and for the carry out. Well, the truth table for a sum is just an exclusive OR. So we just exclusive OR this A and B to get the sum. And the truth table for the carry out is just an AND gate. So we take A and B and we AND them together and we get our carry out. So this is our little half adder circuit. Now it's called a half adder because it's not really of any use in this format, because in order to add more numbers together, that is more bits together, we're going to have a carry in from the previous significant bit. So we'll go ahead and we'll see how we're going to do that. So here's the truth table for a full adder. What we really want is our inputs A and B, but we want a carry in as well from the previous significant bit. So here are our 8 combinations here, and you can read through them and it's quite clear that a 0, 0 and 0 will give us a 0 for the sum and 0 at the carry out, and a 0 and a 1 will give us a 1 at the sum and 0 at the carry out, and the 1 there will give us a 1 and a 0, and the 1, 1, well, it's going to give us a 0 and a carry 1. And you can work your way down through here. I'll let you read them yourself. So finally you're going to have a 1 and a 1. So in effect a 1 and 1 would look like the number 3 in decimal. So the number 3 in decimal, that would be given as, in the binary format, would be a sum of 1 and a carry of 1. So we need to implement this here, this full adder. So let's go look and we'll see how we're going to do that. So this is a process we're going to use here. We're going to have our A and B inputs. We're going to have a half adder with the sum up here and the carry out. So this is going to be the carry out for half adder 1. So if we take the sum from this half adder and feed it into a second half adder, and we have the carry in into this second half adder, then at the output here we'll have a final sum, and the carry out from the second half adder is fed in along with the carry out for the first half adder into an OR gate, and that gives us our final carry out. So let's go and we'll see how that's implemented. So here's the final implementation here. So we've got two half adders. So this exclusive OR and this AND gate is the first half adder, and this exclusive OR and the AND gate is the second half adder, and we have our final sum here, and you can see that the carry outs for both of them head off and go into an AND gate, and that becomes the final carry out. So let's go and we'll see this built and working in Logisim. So if you go into the circuit that's called CPU_adder, so just double click on that, and this is the full adder circuit. So let's go ahead and we'll see how this works. If we get 0, 0, 0, we know we get sum is 0, carry out is 0. So if any of these is 1, if that's 1, we'll get 1 for the sum and 0 for the carry. If that's 1, 1 for the sum and 0 for the carry. Or if that is 1, we'll get 1 for the sum and 0 for the carry. So if we have a 1 and a 1 in here, we'll have a 0 for the sum and 1 for the carry. And Equally, if we have a 1 and a 1 there, we'll get a 0 for the sum and 1 for the carry. Or 1 and 1 there, we get a 0 for the sum and 1 for the carry. But if we've got all three of them are high, then we're going to have 1 for the sum and 1 for the carry. We don't just want to add two 1-bit numbers, we want to be able to add two 8-bit numbers. So let's go ahead and we can see how we can implement that using this full adder. So if you were to click on the next one down, which is CPU adder underscore 8, then we're going to have here our full adder, which is going to add the two 8-bit numbers. So what we have here is our full adder, but there's going to be 8 of them. So if we zoom in, that's simply our full adder circuit. And we've got 8 of them here, and it runs from the least significant bit at the bottom to the most significant bit at the top. So there's a carry in into the first one, and the carry out from one goes into the carry in of another, and so on and so forth all the way up until we get our final carry out. And we have our sums here as well, and they all go together into this splitter. And you can see that we've got our A input here and our B input, and their A's and B's feed into each and every one of these full adders. So the best thing to do is to have a little play with this. So for example, we could start adding some numbers together. So we could add the binary, the number 3, so that's the number 3 in decimal, and we could add a number 3, so that should give us a value of 6. And you've been checking output, that's the least significant bit, so that's going to be a value of 1 and a value of 2 plus 4, which would give us a value of 6. So that's us able to add two 8-bit numbers together. So let's go ahead and we'll look at some of the other functions within the ALU. So let's look at another two functions within the ALU. We're interested in the shift left and shift right. So let's come down to this CPU underscore SHL, which stands for shift left. So if we double click on that, now let's go ahead and we'll see how that's going to work. If we've had our inputs all at zeros, our output would all be zeros. But if we take the least significant bit and we make it a 1, you'll see that in the output, that least significant bit has been shifted 1 to the left. So it's now 1 significant bit more. So similarly, if we were to put in any figure in numbers here, so if we put this one in here, you can see this number here, it's been shifted to the left. And you can see how this is done. We've got an 8-bit register, another 8-bit register. The output of this register feeds into the input of this one here. But in this intervening stage here, what we do is we take a least significant bit and we shift it in. So that's us shifting this least significant bit in. And we take a most significant bit and we shift it out. So we can look in, another thing to note here is that this register that we're using, we're not interested in the set and enables, we can just tie both of those high. So this in effect just looks like a pass through from this point here straight through to this point here. So similarly we can look at the shift right. So if we head down and look up the SHR, so we'll double click on that. And we can see that we've got a very similar circuit, but the difference is now that the input here, it will get shifted to the right. So you can see we've got the input here, that's the most significant bit, and it shifts it to the right, so that's 1 significant bit less. And you can see all these, they all just get shifted to the right. And you can see again how we've done that. We've got our two registers here. The sets and enables are tied together because it's just a pass through from this register straight back through to this register. But at the intermediate stage here, what we do is we can shift in a most significant bit and we can shift out the least significant bit here. So that's all there is for the shift left and the shift right. So let's go and have a look at another useful function within the ALU. So let's have a look at some of the Boolean logic functions we've got in the ALU. So we have our not function. So this is quite simple. It just takes an input in and it gives us the complement out. So it's just 8 NOT gates. So that's quite straightforward. We can also look at the AND function. So similarly, the AND function takes two inputs and it ANDs those two inputs together. So let's go ahead and we'll simulate that. So if we were to AND the least significant bits, we get an AND function for that. And again, we do the rest of these. We'll see the output going high when both inputs go high. We also have our OR function. We double click on that, and again we've got two inputs here, and we've got 8 OR gates, and these inputs get ORed through to this output. So either A goes high or B goes high, and it gives us an output, or both go high. So that's our OR function. So now let's look at our exclusive OR and comparators. These sit together. So we'll go down to this here, which is CPU underscore XOR underscore LE underscore 1. So this is just a 1-bit version of this. So let's double click on that and we'll have a look. So this really is performing 3 separate functions here. It's given us an exclusive OR, so that's exclusive OR between A and B, and that's the output fed through from just a simple exclusive OR. But it's also telling us whether both inputs are equal, and it's also telling us whether the value of A is larger than the value of B. So let's quickly work through this. If A and B are equal, so for example A and B are 0 and 0, we go through the exclusive OR here, and there's a little NOT gate, and it goes into an AND gate. So that point there will be high if both of them are equal. So for example, if it was 1, 1, then that point would be equal. If they weren't equal, that point there would not be a high, it would be low. So let's take, for instance, that both of them are high. So when A and B are equal, then this point here is equal. But remember, we're only doing this for 1 bit. There's going to be another 7 bits. So in order to work out whether there's actually equality in the whole 8 bits, we have to work out whether there's equality for the ones above. So if there is an equality for ones above, it means that there's going to be a 1 coming from the significant bits above. So if there is a 1 coming from the significant bits above, that means that from above all our significant bits are equal, and this bit here is equal, therefore the whole 8 bits would be equal, and we would get a 1 here. So let's look at what happens when A is greater than B. So in this instance here, when A is greater than B, the exclusive OR will give us a 1 output here, so we get a high output into this AND gate. Now we're testing whether A is greater than B, not B greater than A, so we'll take the output from A into this AND gate here as well. Now we'll also have to know about what's happening with the previous bits. So if all the previous bits are equal, but in this case A is greater than B, then we know that all 3 of these are going to high, so it means therefore we're going to get A is larger. Also, if the most significant bit is larger, it doesn't matter what's happened with the least significant bit, this is always going to be larger. So even supposing B is larger than A here, this is a least significant bit, and the higher significant bits take precedence, and it means that the entire 8 bits is going to be larger. So that's a awkward little logic section, but take your time and work your way through it, and convince yourself that it does indeed give us the correct values. So what we're interested in is taking 8 of these and doing it for 2 8-bit numbers. So you'll see that in this section here, CPU underscore XOR underscore LE underscore 8. So if you double click on that and open it up, and you can see that we've taken 8 of these instances here, and they've just been drawn out as exclusive OR. So if I drop down inside, that's just that instance that we've just met a second ago. So now we've got the 8-bit version of this. So let's talk our way through this. So we have our two inputs, our A and our B. So these are our 8-bit inputs. We have our output here, which is just our exclusive OR for these two 8-bit numbers. We also have our equal value here. So this is our output that tells us whether both numbers are equal. If they're both equal, that goes high. And we have another output here called larger. So if A is larger than B, then this one goes high. Now also note that in order for it to work properly, we have to tie one of these to a 1 and the other gets tied to a 0. So let's go ahead and we can see that working. So if you can see at the moment both of them are equal, and we can see we've got a equal value here. So if I change this and make A larger, you'll see it goes to A is larger, they're no longer equal, and this value here, there's a comparator output for this as well. So if we were to take these three, and you can see that A is larger, but then again if we make that equal again, and you can see it's went back to an equal value. So that's all there is for our comparator and the exclusive OR. A bit of work involved in that, so take your time and work your way through it. So the very last function that we're interested in is the 0 function. So you can click on this CPU underscore Z, and this is a simple little function here. All we have is an A input OR gate tied into a NOT gate. So the way this works is when all of the inputs are low, we get a high output. But if any of one of these inputs is high, we get a low output. So we're just using it really to tell us when all of the values of this input are equal to 0. So we're finally in a position to look at the full ALU. So if you come down to the CPU underscore ALU and double click on that, now I'll zoom out in order for you to see it properly. So all we have here is our functions which we have seen in the previous section. So we have our adder, we have our shift right, we have a shift left, a NOT, an AND, an OR, we have an exclusive OR with an equal or A is larger, and we also have this 0. So these are all of the functions that we have just had a look at and designed. Now in order to choose which function we're actually going to use, we're going to use a 3x8 decoder. So we'll have 3 inputs here, A, B, C, and those will give us 8 possible outputs, and those outputs are we're going to use those to choose which particular function gets passed to the output. Now that's simply done. All we need to do is the output for each function here. So let's take, for example, we take the OR gate. So the OR goes to an output here, but it will only pass to this output whenever this value here goes high, and whenever that goes high, that's determined by this value of A, B and C. When it goes high, this little section here will go high and it will pass it to the output, and all that is just an enable section. So if we drop in there, that's just our little enable section which will pass this here to the output whenever the enable goes high. So we've got these here, the 1, 2, 3, 4, 5, 6, 7 of these are used in order to choose each of these values here, or these functions within the ALU. So you'll note that not all of these functions here use both the A and the B inputs. So the NOT function doesn't use the A and B, it only uses the A input, and the shift left and shift right only use the A input. but they also have a carry in, and so does the adder section have a carry in as well. Now there's three other points here. There's the shift left, the shift right, and the adder section. They also produce a carry out, and this is the carry out here, and there's a final carry out for the circuit here. So there's three possibilities for carry out. So each of these have to go through an AND gate, and each of them is chosen dependent on the value for this AND gate. So if we take a copy of this value here, this line up to this AND gate in order to pass the carry out for the adder, and we've got here, we have our AND gate here, and we've got a value coming from this line here in order to choose this AND gate for the carry section for the shift right, and similarly we've got a carry section for the shift left. So these three AND gates here and this little extra bit of circuitry is just to pass the correct carry out from the ALU. So let's go ahead and we'll play about with this and we can see some of it working. So we want to enable the simulation, and I suggest you download and have a wee play with this yourself. So at the point 0, 0, 0, we have a 0 here, and we're already sitting in the addition. Okay, so if we were to add two of the numbers together, so there's 1 and 1, and you can see the output here, we get this output here, and we could also put a higher value in, and we'll see that we're going to get our higher value coming out here. But if we were to put a value in here that's going to be a greater value than the summation of these two 8 bits, it means that we're going to have a carry out. So there's a carry out appeared here. So again, you can go through and you can test the rest of the functions here. So for example, if you wanted to test the larger section or the exclusive OR and the comparator, so you would have to go in and choose that particular input, and in order to get that input we can see, let's see which one it's going to be. So this is the value here that's going to give us the comparator, so we're choosing the comparator here, and we're going to put in two numbers. So when both of them are equal, so both the numbers are equal, we have this equal coming out, and if one is greater, if A is greater than B, we'll have the larger coming out here as well. So there was a lot in that video today. The last thing we need to do here, just before we leave, is just have a look at the instance for this. So if we go into the main section, and then you can pick out your CPU underscore ALU, and this is the ALU here. And now you should understand where each of the pins and what each of the pins do. So we're going to have our inputs here, which are going to be A and B. We're going to have our inputs here that control which function we're going to have chosen within the ALU. We're going to have our carry in, a carry out, an equal bit, we're going to have a greater than bit, and we're going to have the exclusive OR and also the 0. So that's all our functions here within this ALU. So thank you for listening to this video. I'll get you on the next video. Goodbye.